Microphone decomposing. All right, so that one should be good. Extron should be good. Is anybody able to hear me on there?
We can.
Right. Fantastic. All right, what time we got? 12:04. We're rolling late. All right. Well, let me see this way. Nice. I'm going to turn you. I don't know how much you guys are going to be able to see me, but I'll be in that general vicinity. All right. Thank you guys all for coming. Today I will be presenting the work I did during my doctoral time here. The title of the work is A New Paradigm for Film Dryout in Annular Two-Phase Flow. So first, a little bit about what we do and who we work with. So we work with the Naval Nuclear Lab, and I work in the Multi-Phase Flow Visualization and Analysis Laboratory on campus. And we study two-phase flow, and we're interested in the physics that govern the two-phase flow phenomena. So first things first, I looked online, like how you're supposed to give a defense. And first I'm supposed to brag about my publications. So here's me bragging about my publications. This is the stuff we're going to talk about today. And then I also happen to get an award this year. I got Best Paper Award at the NERETH 20. And so that will be a part of this today. Thank you again. Let's hold applause till the end, all right? All right, so a new paradigm. First of all, I didn't name the paper. You can thank the Frenchman, Jean-Marie, who's on there, for giving it its fancy title. But calling something a paradigm, that's kind of a bold move. So what is a new paradigm? Well, a new paradigm implies a shift in how we think about something conceptually. A new information is brought to light, and it changes basically how we view some sort of concept or how we approach something. So, bold claim. Well, you should be asking, what's a current paradigm? What's wrong with it? And what information do I have to show that there is a new paradigm, that we should change a paradigm? So that's what we're going to talk about today. All right, so introduction is just a little bit of description of our work, and then some basic nomenclature, some definitions, and then we'll get into fun stuff. All right, so I was told not to use a laser pointer because it's not going to show up, but I'm going to use a laser pointer anyway. In two-phase systems, especially when you're starting with a subcooled liquid at the inlet, so you start here, and this is heated, a heated channel. So it goes from being a liquid, as you vaporize it, goes through a series of flow regimes, and eventually into this annular flow regime here. This is going to be a topic of our conversation today. But you do reach a certain point where there's this boiling crisis, it's called. And this is associated with a severe reduction in heat transfer coefficient. This is very bad for something you want to keep cool. And what this looks like, well actually, why do we care? Well, if I take that and I turn it around, flip it on its side, stack a couple of them together, basically this is what a boiler looks like. This is a nuclear reactor, essentially. You have water coming in, steam coming out, goes to a steam turbine cycle. So this is a figure from the DOE that they posted on LinkedIn. And I thought this was funny. This is kind of analogous to Dressler's figure that he showed from a Magic School Bus book. But basically, all the stuff we're going to talk about is right here. It just goes poof. It goes from liquid, poof, to steam. But that poof doesn't happen. It's actually a transition of regimes. There's a lot of cool stuff in that poof. So we're going to talk about that poof all day today. All right, so back to this type of figure. So what does the boiling crisis look like as far as our experiment goes? Well, here I have temperature. So this is difference in temperature. This is actually superheat. This is what this is called. Versus heat flux, so heating power. So for every data run I've ever run, I heat, and then at a certain point, I can no longer dump heat into that fluid, and my test section starts to heat up. And you see that with these runaway temperature conditions. So every time I have a temperature pop up, I've reached what's called critical heat flux or critical boiling transition. We're going to call them, So the nomenclature is also inconsistent in the literature. So I'm going to use critical boiling transition and CHF as equivalent names because everybody seems to. But at some point, us nerds should get together and figure out what to call these things. Huh? Needs to be moved up a little bit. Oh. Sorry, guys. Where's my mouse now? Hold on. This is what happens when you get a big lecture hall instead of a nice little conference room. Okay. So
Roman, can you hear me?
we're going to go you, share, and we're going to share you. Share. How did you know that? Okay, Joe. Confirm that. All right, thank you. All right, so you guys missed like the most important stuff, so might as well check out now. But basically, so there's two types of boiling crisis, or critical heat flux, or critical boiling transition. There's two ways that this can really happen. One is at the top of the reactor or the boiler, and one is at the bottom. So the one that we're concerned with is this dryout, and that happens up here at the top. And there's also what's called departure from nucleate boiling, and that happens at the bottom of the reactor. So dryout happens where you have evaporative film boiling, and departure from nucleate boiling, or D&B, happens when you have nucleate boiling as the dominant mode of phase change. But again, we're going to focus today on dryout. And the reason this is important is because most of these flow channels are actually annular flow. So this is from Jean-Marie Lacour. He was a Westinghouse engineer. And he runs these simulations with this like wicked cool proprietary software for boiling water reactors. And this is a simulation for a boiling water reactor that he ran for this year's NERETH paper. But as you can see, if the entire flow channel length is 3.5 meters, I start annular flow at 0.6 meters. That means like 85% of the channel is an annular flow. So that's why dryout, and understanding dryout, what causes dryout, basically how to control it, if you can. That's why this is very important. All right, so what is the current paradigm? Well, the current paradigm and the current proposed mechanism is a critical film thickness. Basically, the film gets to a certain height, and it just poofs. This is analogous to my poof earlier. So in the way that this is modeled currently, it's a 3-field model. Basically, I have the film here just smoothly transitioning to 0. And then there's these critical film thickness correlations, and these are needed in order to make calculations for like reactor codes. There's another way to do it, which is maybe just as arbitrary. But basically, so these here, Mephisto T, GRAMP, and SCADOOP, are reactor codes, basically thermohydraulic codes. Mephisto T is the Westinghouse proprietary one. I think GRAMP was built by Imperial College, and SCADOOP is an Indian company, maybe. But this is the criteria they have set for dryout, just that the mass flow rate is some arbitrarily low value. This doesn't tell you anything about physics. This doesn't actually like help your prediction. You're just saying, okay, it's so small that I probably don't have film there. Okay, hopefully not, or hopefully that works, you know, but you're not really telling me anything about what's going on here. So this does work, and you can iterate through this and make sure that you like reach an appropriate level. But because we don't know the mechanism and we don't know why this is actually happening, we always have to kind of like stay back from our optimal operating conditions. We can never really push it because we don't want to have a nuclear accident. All right, so I want you to think of this poof and this poof as being analogous. And we're not going to think about it this way anymore. We're going to talk about the film as a different construct rather than just a continuous liquid film. All right, so here, that's not supposed to play. So really what happens is you have a film that's comprised of basically a base layer and a wave layer. And as you propagate downstream, you end up with this intermittent dryout. It doesn't just go poof. You have wet, dry cycles. And so understanding how those work, understanding how long it can be dry, how long you need to be wet before heat transfer is completely degraded is really important. So that's what we're going to talk about. So first we're going to go through a timeline of our work. Then I'll talk through the facility, and we'll look at some measurements. All right, so the MFL timeline. Perfect. All right, so when I arrived in 2017, to date myself a little bit, we had just taken over for a professor that had left. And the professor that had left, Tim Shedd, was an established professor in the two-phase field. He had already published papers, significant papers, about droplet entrainment, velocity rate, like velocity distributions in the liquid film. They had already made the lab an established place that performs good science. But when we got there, it was bare bones. It was me, Argentile, Jason, James, Simon, and Dress. It was a bunch of hooligans who had no idea what they were doing. So we get there, and the way I get my foot in the door is Dressler, as we're leaving MATC one day, we're sitting at a table, and he's like, man, I need a plumber in my lab. I was like, my dad plumbs. My dad's a plumber. Having no real plumbing experience myself, but I was like, dude, yeah, totally. My dad's a plumber. I could do it. And so he's like, all right, fine. So he brings me in, and then we get another graduate student, Brian Farrant. Is Brian Farrant here? No? But he comes in, and basically he took a lot of time to make sure that the structure was good. He also implemented these optical techniques and made sure that they were also like measuring what we needed to measure. He spent a lot of time in CAD, thankfully, because I hate that CAD. But like did a lot of stuff to basically improve the integrity of the facility. Then we had a visiting scientist, Tiago, come from Brazil, and he was just described to me as just some kid from Brazil is going to coming out. And so he gets there, and it turns out he's like a wizard. And he knows two-phase flow. And so this was the biggest thing. At this point, from here, we were still just a bunch of guys that kind of knew what we were doing. We didn't know if we were measuring stuff right. We didn't know if we were like running the right sort of conditions or anything like that. And what really Tiago brought to the team was validation. He had been through this before. He had worked in a lab that had done these experiments, had published good work, and he knew how to perform these experiments. And so this is a really big step. This is us stepping into the big leagues. So this ended with Tiago publishing a paper that measured wave velocity in annular flow. So after that, we kind of took off. We had a big paper in 2021, and then I've had a couple papers since then. Jason's also got one in the works, so we've got 3 or 4 publications coming out. It'll all be 2024. It says 2023, but these will all be 2024, except for the Nerith one. But basically, yeah, now the lab is established. We're doing good science. We're known for doing good science. And so let's talk about science. All right, so this is a schematic of our flow facility. We're going to start from this storage tank here. And basically, there's 2 separate circuits. One circuit has liquid that gets injected into the loop as liquid. And the other has liquid that eventually gets vaporized and injected into the loop as vapor. They mix, and we get a known vapor quality. So starting here at this mixing T, I mix superheated vapor, subcooled liquid, and I get an outlet mixture with known vapor quality. This then enters the test section here. So our test section itself is 2 big glass slab walls. Actually, this was designed by Chris Rushmore, this guy right here. Phenomenal job. This is still in use today. 2 big glass slabs, and on the inside of the glass slab, there's a tin oxide coating. We apply a current through that, and then that allows us to heat. But along the test section itself, it's fitted with pressure measurements, differential pressure measurements, and temperature measurements. These are all process condition measurements. We also have non-invasive measurement techniques that we use. So this helium neon laser and this little film thickness ring are basically used to measure things from external to test section. So we're not probing the film, we're not disrupting any sort of flow, we're actually measuring it from outside of the test section. This is a physical picture of what it looks like. It's a bit of a mess. But this is right here where those little optical array is. This is the whole optical tray. And then this is like looking underneath it. So this is the entire length of the test section. It's about 1/2 meter long in heated length. And the hydraulic diameter is 18 millimeters. No, we're good. All right, so how does heat get input in the system? We talked about this a little bit. But basically, cheers. There's a tin oxide coating, and we apply a current to it. Some of the heat goes into the working fluid, some of the heat escapes to the surroundings. We account for this by using basically a thermal resistance network and an energy balance. We can go through that more later if you guys are actually interested. The film thickness measurement works by shooting a laser at a mirror and then through another mirror that's got a hole drilled into it. Then I have a camera mounted up here and I'm looking down so I can see this little ring here. And what happens is I shoot this laser beam, it hits a diffuser, it diffuses into all different directions, and then based on the liquid film height that's at the wall, there's a ring that changes in size. So I can then take the size of the ring and correlate it directly to the thickness of the liquid film. And so here's what this looks like in video form. I'm not sure how good this is going to look. Yeah, so not super sexy, right? But basically this ring changes, and then we're able to get this kind of information. So these are liquid film thickness measurements, taken at different heating. So here, starting from the top left, working towards the right, I'm increasing heating power. So this is no heating power, and this is to the point where I've reached that boiling crisis. But as you can see, we can get really good resolution on liquid film thickness. So the other non-invasive technique we use is an optical technique called laser thermal reflectance. And this was originally made so we can measure temperature. Basically, we bounce a laser off a mirror, and it goes through this polarizer, and then we have a control diode. So we measure the intensity prior to entering the test section. It goes off another mirror into the test section. This right here is actually this portion over here. Once it goes to the test section, it goes through a prism, and then eventually goes to the interface where there's a fluid and the glass. And depending on the fluid that's at the interface, the amount of intensity we get back changes. So if the refractive index is such, that changes how much intensity we get back. So this was from the actual publishment of Brian. So this is 2020, I believe. This was his paper. And we can directly correlate this intensity ratio. So it's the intensity leaving the test section divided by the intensity entering the test section. We can correlate that directly with temperature. That's awesome. We can measure the inner wall temperature without having to stick a probe in there. Super cool. Well, I'm kind of a simple guy. So I figured, well, we could also use this as just like a binary signal. So basically, if I have liquid at the wall or I have vapor at the wall, that signal changes dramatically. And it does so like this. For liquid, when I have liquid at the wall, a lot of my light that I shoot in is absorbed into the liquid. Versus if I have vapor at the wall, most of it's reflected back. And so I measure almost the same intensity that I had entering the test section. So you can think of these points down here as wet. I dry out, I'm dry up here, and then I re-wet, and it goes back down here. Using this binary signal and time binning, we can get an average temporal dry fraction. So F dry, we're going to call it. And we're just going to say that's the cumulative dry time over the total time of each bin. So it would be the time up here divided by this entire length here. All right, so now let's look at some actual results. So this is a typical data set. This is just an example data set. And this is going to take a minute to talk through, so we'll get through it together. It's a lot going on. But basically, I have, on the x-axis, I have time. Sorry, I'm just showing you guys my butt. I have time on the x-axis, and right here on this y-axis, I have heat flux. That's the black line. I have intensity ratio. That's the beer colored. And then over here on this y-axis, I have temperature. The red temperature is the external thermocouple. This is a proxy for the inner wall temperature. The blue line is the saturation temperature, and that's measured just using a pressure transducer at the measurement location. So starting at the beginning, I'm doing the butt thing. Starting at the beginning of the data set, here, we're not heating. So we have 0 heat flux. So the wall temperature and the saturation temperature are effectively at ambient. That's also a nice part about using the working fluid we use, is that we can work at ambient conditions. So I bump my heat flux, and I see a response in the thermocouple. It's good. I continue to do so, and then at some point, the thermocouple, the temperature, no longer responds even though I'm increasing heat flux. So the heat transfer coefficient, so that the actual amount of heat the fluid can take from me, is increasing. Until I get to this point over here, where I bump it just a little bit, and now I start to see this big rise in temperature. This is associated with dryout, critical heat flux, critical boiling transition, whatever you want to call it. And then eventually you keep bumping heat flux, and you get to a runaway temperature condition. And this is bad. It's not ideal for any component. So we take that data, and we look at some time average data first. So on the x-axis here, I have local vapor quality. On the y-axis on the left, I have heat transfer coefficient, and that's in black. And then on the y-axis on the right, I have the temporal dry fraction, that F dry we talked about, and that's in red. This is in a log scale. So down here, there's no points because it's 0. I haven't dried out yet at all. So as you can see, for increasing the heating power, basically my heat transfer coefficient stays the same. And then I get a little bump, and then I get that degradation. Well, coinciding with that little bump is the first indication of dryout. So I'm actually losing liquid film and increasing heat transfer coefficient, which is counterintuitive. The whole idea of annular flow is that the liquid film is what governs the heat transfer coefficient. Losing that would just go back to single-phase vapor, which is much less than the two-phase heat transfer coefficient. So this is typical of every data set we've taken. So in order to compare data sets with differing mass fluxes, we normalize the heat transfer coefficient. That's this big H. This is the normalized heat transfer coefficient. And it's taken as whatever we measure minus the vapor heat transfer coefficient divided by the maximum heat transfer coefficient prior to dryout minus the vapor. It's just a normalization. And then there's some weighted normalized heat transfer coefficient. And we use this just for a comparison. We have no idea how this is going to act. So this would be if the heat transfer coefficient decayed linearly with dry time. Well, that's not what I get. I don't get this linear, that would follow the black line. I don't get a linear transition. And I also get an increase in heat transfer coefficient, some high is like 25%. And so this happens right around F dry equals 0.05, so 5% of the time. So when I'm dry 5% of the time, I have the peak heat transfer coefficient. Okay. So along with those data sets too, I told you we could take film thickness. So what happens at the end of these film thickness measurements is that they kind of stack up into these waves. So this is steady state, and they still end up looking like these quasi-periodic waves. And I see a wave pass very regularly, even though I'm not forcing anything. There's no forcing function. I'm not like pulsing, not doing anything like that. But there's some wave function that's developing. So we're going to investigate that by now forcing the frequency. Let's see what happens when we force the frequency. So in order to do that, we added a pulse generator, which is a fancy name for a big saturated tank. Basically, we boil a refrigerant in here, we send it downstairs, and then we have a little PG Mini, I call it. It's a little vapor capacitor. It's got a little whistle valve that we roll a cam to open and close. That, oh, do I have a, yes. Okay, so then I give the transient vapor mixes with the steady state vapor. And then they both mix with that liquid, and then that goes into the test section as a two-phase mixture of known enthalpy. So same thing, except now we're adding this extra pulse. Okay, similar type of data sets. And now we can actually run longer. So now that we've made the facility a little bit better, We have a little bit better control. We can actually operate for longer data sets. So if you look, this is an hour-long data set. Each one of these black lines, these black vertical lines, indicate where I took liquid film thickness measurements. And so I can really see from all these measurements the evolution of the film as we heat. These are, again, time averaged. So this is the same thing, heat transfer coefficient and F dry as a function of vapor quality. The same behavior we saw for the steady state. And then over here, I have just time averaged data related to liquid film thickness. So I have the mean, the wave height, and basically the minimum. What was interesting, though, is we saw that for every inlet condition, that for large amplitude, low frequency pulses, 1 hertz, half hertz, something like that, we saw a big dip in our CHF, or basically the heat flux that made us go to runaway temperatures. But then once we had high enough frequency pulses, it went back to being pretty much equal to steady state. So these big pulses, which they have some sort of effect on the flow, and we're not quite sure what that is at this point. Well, let's investigate. So this is for half hertz pulses. So if you look closely, each of these time traces, it's about, 2, 4, 6 seconds. We have now controlled the disturbance wave frequency. So by sending big enough vapor pulses, we can actually manipulate the disturbance wave frequency. And the disturbance wave frequency tends to actually matter when you're talking about drying out or critical heat flux. Another cool thing that we can do, I'm not going to talk about this really much, but basically we can take PDFs of the liquid film thickness measurement. And there's a change that happens. So this is unheated, increasing heating power, all the way to the point of dryout. You'll notice here that I have a log normal. So for you guys that aren't math nerds, that just means instead of a normal bell curve, I have a bell curve with a tail. And then it transitions to more and more normal. So basically, I have more and more of a normal wave function rather than a big wave, and then just like this. All right. So we take a look at the heat transfer coefficient normalized. So this is actually the nominal value of heat transfer coefficient for all the pulse data. And then here's the normalized values. And then I have them plotted here as a function of pulse frequency. But this one is what we're going to look at. So we're going to take this and compare it with our steady state data. Well, it agrees. So for some reason, 5% of the time, I reach this critical heat flux, or this optimal boiling condition, or this peak heat transfer coefficient, at 5% of the time for no matter what condition I have. There's another comparison. All right, so we're calling that then OBC. If you really want to get into nomenclature, read my papers. I'm not going to get into that too much. It's very boring. All right, so now here's the fun part. So what the hell is going on? Well, let's take a look. Oh, did you not play? Come on, guy. There she goes. All right. So this actually captures a sequence of dryout and re-wet. So we have the flow going upwards in the channel right now, and this is all liquid. We're looking again through the heated surface, through a glass window. There's a bunch of these surface features present, these ripples, and as we get thinner and thinner, we're heating, they start to diminish. So much so that at this point here, there's like almost none. And then that's where we get our first dry patch. So the film completely evaporates down to the point where it's so small that I can't have any sort of oscillations on the surface, and it dries out. The dry region grows, it coalesces with another dry region, and now I have almost my entire test section is dry. So in order to re-wet, I need some sort of liquid to come through. Well, it does that in the form of a wave. So this blue line here represents just a wetting front. The wetting front moves upwards, but it's slowly decelerating. And then at this point here, it's pretty much stalled. I also change the frame rate because this happens very quickly. Here's a big disturbance wave. This comes and this catches this wetting front, it has enough momentum to force the liquid over the wetting front and to re-wet the heated surface. And so this is the actual mechanism for dryout. This is how dryout happens. There's no critical heat flux, there's no critical film thickness. It's the wave re-wets, the base film in the wake of the wave dries out. That's as simple as it needs to be. You don't need any sort of correlation. You don't need to estimate some critical film thickness. It's really dominated by the disturbance waves. So with that idea, can we describe that mathematically? Well, if I say take T wave as just the wave period, 1 over the frequency, and then I relate that to the F dry we talked about earlier, I get this expression here. So then I'm going to take this, plug this into here, and I'm going to solve that for vaporization temperature. So if I did this energy balance on just a chunk of liquid, I would calculate how much time it would take for the liquid to vaporize with some corresponding heat flux. And I get this expression right here. I rearrange that a little bit, put F dry in there, and this is the final expression here. So I have heat flux is equal to the density of the fluid, the enthalpy of the vaporization, times the wave frequency, the base film thickness, and then how much ever dry you want. This just relates to the extent of the dryout. So is it 5%, 1%, 10%? This is just related to how much dryout there is. For these measurements, like I said, we noticed a peak heat transfer coefficient at 5%. So that's what I compared it with. I put in F dry is equal to 5, and I compared it with my experimental data here. As you can see, there's pretty good agreement. I couldn't force a correlation to look this good. And so this agreement confirms the postulated mechanism. So the new paradigm is really the wave base layout of the liquid film and the treatment of the disturbance waves as such. So how is this going to impact the world? Well, immediately, people can update their nuclear codes. Like they can actually make their operations safer. Like literally, Westinghouse and GE can update their codes to reflect this. They don't need to now estimate a critical film thickness. Now they need to now worry about wave frequency and base film thickness. So it immediately increases safety factor. In the future, we can use the physics and use it to our advantage in design. So we can design things that take advantage of this mechanism. Say you have something that can dry out a little bit, or you want to force dry out a little bit because you get that increase in heat transfer coefficient. You can set up an array of pins and force dry out to happen in a certain way. You can actually use this to your advantage. So for the design guys, you'll figure out how, but that's not really my forte. So this is really the big impact of what we did. And the next, I just have some thank yous and some pictures. So this was taken in Jessler's backyard. This is basically our whole team from way back in the day. And then there's a lot of these. So yeah, thank you the entire committee. I'm not going to go through all this, otherwise I'll start crying. But thanks to all these schmucks, and especially these schmucks. Thank you to the ME faculty, who has just been great to work with. And thank you to my family and friends for supporting me through this. And obligatory references slide, and thank you very much. That's all I have for you today. Thank you. Any questions?
Hey, Roman, can you hear me?
Yeah.
Hey, Roman, this is Tim Shedd. Great job. Very cool. Don't know if the audience can hear me at all, but you can translate.
Yeah.
So one of the things
legendary
that
Tim Shedd on the phone here.
So one of the things that has been known since the time of Hewitt way back is that this critical film thickness is about 5, Y plus of 5. And that's when, I can't remember which paper we published, but that's when we found that the surface waves disappeared.
Yeah.
So it seems like there is a correlation. I was just curious if you found that. I'm sorry, I haven't had time to read your papers.
No, that's okay. This is actually future work. So you gave me a perfect segue there. So this is every single data set I've ever taken. And I have this plotted as a function of film thickness and vapor quality. And this looks like a friggin' mess. But if I take it and I normalize it using wall shear, I get this. I get the base film thickness is certainly on the order of the viscous sublayer. And basically, it provides just that lubricating layer so that the waves can continue to be turbulent and propagate downstream. And so it just serves as a lubrication layer. So I think that the observations you guys made are identical to pretty much what we're seeing here now too.
Cool. Awesome. Thank you.
Yeah.
Great job.
Thank you.
Very cool to see this.
Oh, total internal reflection. Yeah. All right, we'll go back. Should have just taken Jason's for this. All right. Total internal reflection. Of course, the nerd would ask a question about this. All right, so what happens is, there we go. These are all Thiago's figures, by the way. So a laser beam gets directed towards the test section, normal to the test section. Hits a piece of diffusing tape, and then when it hits the diffusing tape, it spreads in all directions. Then it gets to the inner layer of the wall, where there's either vapor or liquid refrigerant. Depending on the state, but then also depending on the height, it reflects back. So the higher the height of the liquid film, the more it reflects back in this general direction. So I have a bigger light ring. So that goes like this. So if I would have a thicker film, this light ring would increase in size, versus if I have a thin film or no film, I would just have when it's dry, that's what we use to calibrate it with. But and you can calculate that just using Snell's law. Yeah. Yes, sir. Why was I interested in this? Well, that's funny actually. This is twofold. So one, because I worked in the lab, and I just wanted to get in the lab. I just wanted to do research, and then I started to think it was cool and cool and cool. And two, the reason that this got so deep. Well, let me see if I can go back to my nice, handsome plots here. The reason this got so deep is because of the vagueness that we were asked to write a report from the Naval Nuclear Lab. The task was write a report on CHF. At that point, if you read my first paper, there's 10 different definitions for CHF. So I had to go through and find out what I thought CHF was. And so the vagueness at which we were given the task, and then also our sponsors' willingness to just let us science and just let us kind of look at what's interesting, and not really force us to go any which way. Just tell us, hey, if you find something interesting, follow that path. We've worked with a really cool guy, Evan, at the NNL, and so that's what really led to this. Was I started to see this behavior, and it was weird, and I like weird, and so I just kept digging and digging and digging. Yeah.
A lot of work went into your whole project.
Yeah.
Is there anything in particular that you're most proud of? Or?
That I'm most proud of?
Yeah.
Why you gotta do that? Yeah, I should have thought about this actually. That I'm most proud of? Yeah, here you go. So this, first of all, this is pretty cool. But what am I most proud of? This. Working with these guys. Getting the opportunity to work with these guys, these guys, these guys. Literally having the opportunity to work with so many brilliant minds and having so many different kind of thought processes and different strategies and learning from, I mean, you know, Jason's a technical wizard, you know, and can do things that I could never do. And learning from him and like growing from all these guys in many different ways is really, I think, your name should be up there. Sorry, dude. I'm going to check. Any questions on the WebEx end?
I do have a question. Well, okay, go ahead. Oh, I would ask after.
All right. Yeah, thanks. Hey, Roman, this is Evan.
Hey, Evan.
So I have two questions, kind of. You had mentioned that in your plot of the heat transfer coefficient versus dry fraction that you see a maximum. Could you say something for the first question about how the instantaneous maximum compares to, so you said like 25%.
Mm-hmm.
But when you look at that as a function of time in one of your papers, could you just say something about the instantaneous maximum in heat transfer coefficient?
Yeah, absolutely. So a big part of what we do, these are your bonus slides too, that's a good segue. A big part of what we do is not fix typos. But a big part of what we do is we wanted to take this mechanistic approach to modeling. So basically, there's, in real life, so here, let me go back to, okay. So in real life, how this is typically done is I give you a set of inlet conditions, I give you a set of like flow parameters, and then you force fit, you take a bunch of data, you force fit some correlation to some big crazy database, and then it spits out, you know, an answer, and maybe it's right, maybe it's not. But really, there's physics, and physics lead to liquid film characteristics, and then these liquid film characteristics have more physics involved, and that leads to CHF, dryout, heat transfer coefficient. So a big part of our work, and specifically Jason has been focused on that part of the physics. Roman has been focused on this part of the physics. So for the heat transfer coefficient model, we were actually able to model it and get an instantaneous heat transfer coefficient. So this is a time trace with liquid film thickness plotted on this y-axis and in black, and the heat transfer coefficient plotted on this axis and in red. And as you can see, there is a change in heat transfer coefficient that's associated with almost drying out. And what's happening is you're making the conduction length very, very small while keeping the heat flux the same. Then once we dry out, we see a reduction where it goes to like a vapor-only heat transfer coefficient, which is on the order of 10 times less than the two-phase heat transfer coefficient. And then it re-wets, and I get a spike, and then back up to this nominal value here.
The maximum that you see is much higher than 25%, right?
Yes, yes, absolutely.
So my second question is, can you tie that in, just speculating, can you tie that into Jason's obstruction wake region for the boundary condition, and does that explain something, the fact that you could generate these very high heat transfer coefficients in the wake and maybe take advantage of that?
So I'll conject for you. I don't know, but I will conject. I do think that, yeah, so I think it's, first of all, you have that wake region that's small, right, behind Jason's obstruction. So just to give everybody else an overview, Jason's running a very similar experiment, except in the middle of his flow channel, there's an obstruction. And it basically resembles any sort of pin inside of like an evaporator coil or any sort of something, a sensor, whatever. And we're looking at the flow around it. And what he sees is basically there's a dry wake in the region just downstream or just behind the obstruction. And Evan's asking how that relates to this. So I think the increase in heat transfer coefficient that Jason sees is partially due to the F dry, but also due to the area being dry, like the area fraction. And then you also get that increase in heat transfer coefficient from that triple contact line. So the fact that he's always got that triple contact line increases the heat transfer coefficient immediately in that region there. And a lot of times it's enough to make up for the lack of heat transfer coefficient in the dry region. Does that make sense?
Yeah. Yeah, it seems like an area to go further, because it's suggesting that your heat transfer coefficient theory, you know, the sort of the development of the heat transfer coefficient model can guide design in that way. You know, you could try to improve heat transfer in these complicated, like increase transverse flows
Yes.
downstream of an obstruction. So,
Absolutely. Or if you have like an electronics, device that, can be, can superheat a little bit, but doesn't have like, basically the rate of temperature increase isn't as high as something as like a fuel rod would be. You can actually let it dry out or force it to dry out in a region so that you get that enhancement by like setting like pins or a spacer grid or a pin grid, and basically, yeah, forcing the wakes into whatever region you want it to.
all right, thanks.
Yeah.
I have a question, Roman.
Yes, sir, Jean-Marie.
In your video, like, if we go back to this video, what is the F dry for that video
F dry of this.
of the waves passing over a dry patch?
Oh,
Yeah.
the dry out re-wet video.
Yeah, that, yeah.
2.5%. I think I'd have to actually look, but it's less than.
Okay, less than 5%.
Yeah.
How does this video looks like if it's over 5%?
How does this video looks like it's over 5%? So that video only captures a single dry out re-wet sequence. What you didn't see was the rest of the video where it was wet.
Yeah, I understand, but meaning I'm imagining that, okay, if you are above 5% and you have more time in the dry region, but is that enough to explain temperature runaway? I was imagining that actually your dry patch at some point will never re-wet.
Yeah, right.
You might have some waves, but actually they will not re-wet the dry patch.
Yeah.
They will go around it if it's possible, or they will go on top of it. Basically, that would be
Like a
Leidenfrost.
Yeah, like a Leidenfrost effect. Yeah, you're absolutely right. So, but the time scale at which the waves arrive, especially in this region here, oh, you can't see my laser, especially in, can I be slick enough? No. Okay, well, where you reach basically the peak heat transfer coefficient, if you increase heat flux and you start to reduce your heat transfer coefficient, that's exactly what happens, is that you get some regions that don't re-wet. And then you also get, every time now, there's a bigger time lag between I dry and I wet, and that allows that region of the wall to become more superheated, which means when the wave arrives, it touches a higher temperature surface, which means more vaporization occurs at that instant. So basically, the waves slow down then too. So once you have a big enough gap between the dry front and the wave front, you get a big enough superheat that you start to then vaporize a significant amount of the liquid from the waves and significantly reduce the velocity of the wave, which is why I think this degradation happens so severely.
Okay, I understand. Okay, I agree with you. I think in your discussion of a CHF happening after a dry of 5%, this needs to be included. Otherwise, it's not enough. There is something missing if you are not including this discussion.
Oh, I'm sorry. Read the paper we wrote together.
No, I'm aware of it. I just wanted to make sure that you have that in mind, because during your presentation, you said, this is CHF, this is governed by the waves, but something was missing, and that was exactly what you explained now. That's why I wanted you to say that.
Oh,
so
okay.
just to make
So
sure
that was a layup?
Yeah.
I appreciate the assist then. Did you have a question? Does anybody else have any questions? Yeah. So it is definitely probably some sort of fluid property, but really the waves are Kelvin-Helmholtz instabilities in their origin. And so the original frequency, especially if we go back to, some of these. So when Tiago measured wave frequency for adiabatic, that would be this condition here, he got like 10 to 15 hertz, 10 to 20 hertz. But then basically what you actually have is stacked wave functions. And those really those high frequency waves get diminished faster. And so by the end, you're just left with these low frequency, large oscillations. So I think it would have to be modeled as a Kelvin-Helmholtz instability to begin with, if you were going to model it physically like the actual evolution. But if you were going to model just the waves themselves at that point, you could start with just stacked wave functions.
So how would I implement this? So, I mean, it works for this test thing, but can I extrapolate that to interaction?
Yeah, absolutely. So basically, you just yeah. So in the Mephisto T right now, they have a correlation for there's a correlation for wave function or wave frequency. That's for water, for steam water, and for delta base. That's for steam water.
What is delta B again?
Oh, delta is the film thickness. Sorry, and delta B is the base film thickness. Yeah.
Which we established by the way.
Once the wave passes by, yeah, absolutely, it has to. And that goes back to this idea here that Tim brought up, is in order for those waves to remain turbulent, they have to like reestablish that base film underneath it.
But the delta B and the frequency are liquid and surface dependent.
The delta B, they are fluid dependent and likely surface dependent, sure, yeah. Although I see a lot of research I see, as long as it's not extremely rough or like an extremely bizarre surface, a lot of these like fluid characteristics are independent of like roughness.
Right, but what's the slide you were having that you had your simple equation?
Yep.
What were you predicting? That.
Yeah.
So if F right is 0.5, I can get rid of the parentheses and it's approximately the same as the data.
Oh, so I don't know. So that's one thing I don't know. We haven't tested this enough.
No, but I got 0.05 minus 1 is 0.95, so that what's in parentheses is just a correction factor. I'm more interested in the F wave than
No, this is not a correction factor. This is the extent of dryout. So this is how much dry time there is.
right, but quantitatively it's 1 minus 0.05.
Yeah, but that's because I set it to 5% because that's what I measured this quantity at. I can set it to whatever I want. I can set it to 0, and then I would just have the exact heat flux that I get dry out at.
But isn't, I guess I'm back with Professor Anderson, isn't F wave and delta B and F dry a function, would have to be empirically found for every fluid surface combination?
For every fluid surface combination, sure, unless someone comes up with a physical model. Yeah, absolutely. Yeah, and so I have also correlations that I developed using, I don't know if I'm going to get in trouble for saying this, but I have correlations that I developed using our data that Tiago took, the adiabatic data, and I fed that to our sponsor guy at wherever he works. And he tried it out on his, whatever he does, and it works. So that's as much as I could say without getting people in trouble, but basically, so the wave velocity, or the wave frequency, is dependent on the liquid film and for sure the vapor. So basically the interaction between the two of them. The base film thickness, same thing. It's dependent on the vapor and the liquid. So you can actually make a pretty easy correlation using the Reynolds number of both of those. And then it would just be a coefficient attached to it. And so instead of having a correlation for Q that is just a bunch of dimensionless parameters fit to some exponents or whatever, really, right now I need 1, 2 correlations, and really I can model these at some point. I'm hoping somebody can model these at some point. These are physical phenomena that we should be able to model it. And there are models for wave frequency if you look at Kelvin-Helmholtz and stuff like that, but they don't give very good predictions, especially because this is heated, and most of the analysis is done under unheated conditions. Does that make sense? Well, please. All right. Anybody else? WebEx folks? Okay, all right. Thank you.
Excellent job, Roman. Thanks.
Thanks, Roman.
thank you all for joining. It's been fun. Let's go to the library after this. You guys are on.
I'll see you there.
All right.
Just want to say, like that suit you got on, Dr. Morse.
Thank you so much.
Engineering just wanted to give you a thank you for all your support to students and just wishing you well.
Thank you so much.
Yeah, this was a pleasure to be here. I appreciate it.
Did you get the award that you were nominated for?
The what?
You never mind. Maybe I just.
Wrong person.
I'm pretty sure you got nominated for an award. Yeah.
Well, I guess we'll see.
I guess we'll see. You too. Thank you. Hey, Axel. This is Justin's dad. This is Chris. He worked in the lab too. He was in that picture in our in the backyard.
Very good. Very nice job. Chris would be proud of you.
Thank you.
He really would.
Thank you. I really appreciate that.
I won't be able to make it to the library.
That's okay.
I'll give you a call. We should meet up next week.
Yes. Thank you for coming, man.
Yeah, it was great to see
It
you.
was a blast to see you. Thank you. Thank you. What's up, dude? What's up, dude? How you guys doing? What's up, dude?
Did you say good talk? Good talk?
You don't have to lie.
They do all. They had a bunch of questions, but they didn't want to embarrass us. They want to say.
Oh, that's okay. What kind of questions you guys got?
Congratulations, Roman. Good
Thank you
job.
so much. I appreciate it. Great work. About your backyard? Yeah.
Alright, guys, you're great in math.
So, you guys, the defense now they have to tell me whether or not I'm a doctor. So you guys have to leave, like 5-10 minutes.
All right, that's fine.
Thanks. Thanks for coming. Thanks for coming. Thanks for coming. Yeah, but it won't take long. I can't imagine.
Hey, Roman. Roman,
They just go, nah.
can you hear me, Roman?
It's like a Caesar.
Yeah, right. Hey.
Graduation gifts and there's my birthday gift that I got you. You'll know which one is that.
Thank you so much. Hi, I'm Roman.
Mom.
Nice to meet you.
I'm Gabe.
Gabe, I've heard a lot of good things about you, dude. Thank you guys for coming.
You thought about asking if you could explain it in my terms.
Maybe announce that they got it.
Yeah. So anybody, hey, sorry, anybody that's not on my committee, can you leave?
Congratulations, man. Oh, you must be so relieved.
You did so good.
Hey, Roman.
I'm so proud of you.
We could do that afterwards. I gotta, like, the committee members, yeah. So, yeah.
You're busy. You need to keep it leave. Great job. You're amazing.
Thank you so much.
Got it. Good job, Roman.
That was awesome. Bye. We're leaving.
Oh, bye-bye.
Very proud of you.
Thank you
Good
so
job.
much.
Can I take this to the bar?
Yes,
All right. I'll go get a table.
good. And a drink for me. All right. Thank you, Lindsay. All right, everybody, get the hell out of here. Look how cute she is.
Yeah.
Thank you.
Did you make congratulations?
Thank you so much. Thank you so much.
I think I caught some of that.
That's good enough. That's good enough. I appreciate it. Thank you.
Congratulations.
What's up, big guy?
How are you?
Good.
You
Thanks for
could
coming.
play with the Badgers. You can walk. You can walk on.
I was playing fives with the old lineman last week. Yeah. Yeah, we're going to the library across the street. That's what I'm saying. I still got 4 years eligibility, I think.
You fucking.
Thank you. I appreciate you guys coming. Thank you. All right. Scatter. Are you guys sticking around?
I'm ready to go back.
All right.
Congrats, dude.
Thank you. Appreciate it. Thank you. Yeah. We'll holler. We'll holler later.
Yeah, I work, so
Okay.
I'm off all day.
All right. All right. See you there. All right, Simon. Get the hell out of here. Oh, thanks. It's not over yet. They can tell me no. Wait. Who? Okay. I'm familiar with the Wheeler. I'm not sure if I know specifically what you're talking about. I know the name.
Reports by Framatome which essentially look at liquid film thickness and a minimum thickness which then is evaporated, which is what I read that to be.
The base film thickness.
Right.
Yeah.
But have you seen any work by Ferrarula on the same subject?
So I've seen this mechanism is not mine. This is postulated by like Hewitt. Like Hewitt was the first one to be like, okay, there's waves and then there's a base region. And it's probably that it's the base region that dries out in between the waves. So this is not my postulated mechanism. Like this is not, up.
But what I understood to be the case is that you need to measure F wave for the time, the inverse of that, reciprocal of that, and the base thickness.
Yeah. And you can estimate, but the thing is you need to measure wave frequency. You can estimate the base film thickness. This is future work using y plus is equal to 5. So typically, if I go even farther, I'll go to actual data set and show. So for a single data set, this is one case. So I took this data set here and I normalized everything. And this is what I got for my minimum base film thickness. So it's almost consistently y plus is equal to 5. So I think it's just Jean-Marie and, well, I guess Cruz.
Can you hear me, Roman?
Yeah. Can Jean-Marie stay, or does he have to leave too?
I'm still here. Can you hear me?
Yeah. Can you hear me?
Yeah. No, because you listed me on the committee, so I'm not sure if I was supposed to join them somehow.
Is it okay if okay? So everybody who's not Jean-Marie or Evan, could you guys leave? And thanks for coming. Love you lots.
All right, man. Congrats, bro. Good stuff.
Thank
Let's
you.
keep in touch, man. Yeah.
So your hypothesis is that y plus equal to 5 is a way to estimate what the base film is?
Based on measurements.
Right, but I'm still back to what Professor Anderson asked about in terms of fluid and surface combination.
Yeah.
So you'd have to check that for different fluids and different surface combinations.
Correct. Yeah. So the correlation in Jean-Marie's 2022 paper that he uses for base film thickness is slightly different than like what I use. But we're building this software together it's kind of like an open source. Jason's actually the lead developer on it, but we're building like an open source two-phase solver, kind of something like Mephisto or Gramp or Skadoop, but we're going to make it open source. And we've already implemented this idea into the code, and we actually get better like agreement between the waves and base than we do if we use like force it to be split into a mass. Like there's certain ways you can do it at the onset of annular flow. You can force it into a mass ratio, or basically you can force this idea. And if we force this idea, we see more behavior from the waves that we would expect, versus if we just like split it into a ratio, then the waves and base kind of act strange.
So that's the hypothesis, is y plus equal to 5 or approximately.
Right.
What about the forced oscillations? Is there a temperature limit at which you, because I don't know if Jean-Marie or Evan asked a question about the Leidenfrost temperature.
Oh, so.
Because there's some experiments that have been done in Germany by the NRC called the Cathy experiments. Are you familiar with those
No,
experiments?
I'm gonna write that down. No, I'm not.
Professor Duarte was monitoring those for the Nuclear Regulatory Commission, and what they found there was that at what they called to be essentially the homogeneous nucleation temperature,
Yeah.
you would not get any rewet. You would essentially get an escalation and an overheat.
Yeah.
So you might want to look at those experimental results.
Yeah, absolutely. Was that in the manuscript that you sent me?
Those were referred to.
Okay. Excellent. Yeah, I definitely will. Yeah.
They essentially are BWR data that were originally, I think it's the BWR assemblies or Framatome geometry.
Okay.
Not Weston.
Yeah, I'll actually.
The geometry is proprietary, but the concept where you see the wet and the re-wet cycle, dry, re-wet, etc., and then the escalation into essentially a runaway occurs based on a temperature.
Well, so that's funny too, because Jean-Marie and I, the critical heat flux term, like I told you, like there's a lot of debate and there's a lot of misuse of it in the literature. And if you look at the NRC's latest report, they actually recommend the CBT and recommend using CBT rather than CHF. But they defined CHF as the point where for every 1 second, there's 10 degrees increase in superheat. None of us really liked that definition.
Very nicely bureaucratic.
Yeah, I mean, but it's also hyper dependent on the system, right?
Okay, but I'd recommend you look at the capping experiment.
Yeah.
This is what the results have shown.
Absolutely. Yeah, thank you. If you have, if you could email me, just because I'm sure there'll be a little.
Well, I would just suggest you, Duarte's, her PhD student, Paul, Harvey, I think is the name.
Okay.
Did some of this work for her.
Okay.
So just contact her.
Okay, yeah. I'll just talk to Juliana. Thank you.
The problem that they had was that they couldn't relate that to different things. So that's why they came up with these other criteria.
Well, and they couldn't measure it directly. So no one's been able to see through a heated surface that's had this long of a heated length that's been able to see these many dryout cycles. So typically when, at least like Tomy, all of Tomy's work, which they have visualization, but the back has a serpentine, so it's like one block has a serpentine heater, and then they have a glass on top of it, and I never see through the heated surface. So.
But they still said, there's waves and then there's this part, but then it came down to how do we model this? So that's still an open question.
Well,
you still have to model the frequency of the wave and the thickness. It has to be very dependent on the fluid and the
so this says that the base film thickness shouldn't be, right? Because I've normalized this now. So this should be not affected by any fluid properties. So for this one at least. But then for wave frequency, if you, but with respect to I guess if I normalize a turbulent boundary layer with air, or I normalize the turbulent boundary layer with water, I still get the same velocity profile. But we're not doing sodium today. But like if you have a crazy different Prandtl number, yeah, for sure. So that would be the exceptions to the rules. If you have a if you have a Prandtl number that's very far from unity, that this is probably gonna require some either heavy modeling or a different approach for sure.
I think where he's going with this is, let's just stick it with water. But if I go from these conditions, which are room, essentially STP conditions, to 70 bars in a BWR,
Yeah.
the density of the vapor is different, so the shear stresses will be different. So it might not be the same film pitch. You'd have to do some.
So we have.
I guess that's what Mark is doing.
Yeah, and let me see if I actually included any of those. So using the solver we have, so we have a bunch of data from BARC. Do you know the BARC? So it's a place in India, and they have a bunch of steam water data, and then we also have a bunch of data from.
Oh, this is the Indian.
Yeah. So we use their data to run the simulations. I don't have any of them with you, unfortunately. But basically, we use and the 3.8, like the first figure I showed that has Jean-Marie's, sorry. Here we go. Back to here. All the way back to the beginning. So here, one more time. There we go, okay. So here, like this figure, this is BWR reactor conditions. So like all of the data that we're using to run the software is typically like a Barks data set. We also have a few other steam water data sets. But yeah, we're using steam water to run like the simulations. At 70 bar, at 1600 kilogram per meter squared second, and at 10 degrees inlet subcooling typically. But so the wave frequencies are definitely a little bit higher, but you'd expect that, right? You'd have higher mass flux, like there's a higher shear at that interface. I would expect higher density vapor have a bigger effect on the liquid to drive more of these waves. So you do get higher wave frequencies, but it's on the order of tens. It's on. I understand how the Y plus equals 5 will help you scale. Yeah. I don't know how you're predicting the wave frequency. I'm not predicting the wave frequency besides using a correlation, but I'm saying what you can do is now that we can, I'm just going to scroll to it. Now that we can, you just hit a number, I can go to this one. Oh, does that work like that? I don't even know. Oh, sure does. Yeah, tricks of the trade. So the wave frequency question. All right, so basically, if we were to go through the 4-field modeling. So now this is basically this is the modeling that Jean-Marie proposed. Rather than a 3-field with drops, vapor, film, we break the film now into 2 components, waves and base, right? So you go through the equations, here are the definitions. Basically, you can work it to this point here. So this is just conservation of mass simplified as much as possible. And the wave frequency is built into basically this term here. So UW, the wave velocity, is really the wavelength times the wave frequency. So I know everything here. Well, now I do. This is droplet deposition. This is how much is vaporized. And this is a transport term that I recently modeled. And so if I'm able to solve everything here, and these are just models, so the droplet deposition and entrainment model either come from, Govan and Hewitt, or Ishii is the other one. But pick which one you like and then stick it in. This is just the amount that's vaporization, or the amount that's vaporized from each field. And then there's a net transport between the 2 fields. So if I know everything here, which I do, I can then solve for this term here. So you're saying the wave frequency is an output of the model? It will be, yep. But right now there's a correlated input here. Right now I have a correlation that so how did I get, is that what you're really asking, is how did I get the wave frequency for that figure? Yeah. Oh, I literally took the figures, the data figures, and counted waves and plugged it in. Like I took, in my master's thesis, I have a ton of figures like this. People in my trade are just trying to understand the limits of applicability of this work and where it stops being, where it falls down. When you enter mist flow or when you're in churn flow. Like it's literally applicable for all the conditions we've looked at, for the widespread from ours, which is atmospheric, we're at temperatures that are near ambient, near atmospheric pressure, all the way up to, BWR conditions. This idea, this concept works. The correlations may differ, for sure, especially for the frequency, because that's not well understood yet. But I think eventually someone will be able to model that physically, and then that entire thing is closed. But I think the last thing you said is the answer. Yeah. I think another thing is what kind of uncertainty are there in stack up? Oh yeah, for sure. Yeah. So does this give you a better prediction? Presumably, if you have really good correlations, it's the error on all correlations that fit with the model. For sure, but you don't know any of the physics. You can't design around that. So that I agree that I could probably make the Greneville lookup table, or I could probably maybe get under certain conditions get a better estimate from the Greneville lookup table than I would from this actual physical mechanistic model. Did you apply your own lookup table to these? It does not perform well for the R245 FA data. No, for the solver, we have it converged to basically, we got exactly that. Like we have a plot where it's within 10% of the Grenville lookup table for the first 15,000 points or something. Sorry, no, I lost my train of thought. Oh, so yes, you could get a more accurate prediction from a correlation, like right now. But the physics and modeling the physics, I think has an advantage in one, future design, and then two, like the more we model, the better we model, the better the predictions will be. You know, I mean, I could curve fit something for like something we already know that's super easy, like gravity or something like that. Like I could curve fit anything I wanted. I mean, I could throw it into an AI model, throw it into a machine learning, let the machine learning curve fit 1,000,000 times, and just spit out a prediction for like CHF. No, and that's a good point. And actually, how this should be treated is a distribution. There's really, like, especially, you don't have just one wave frequency. Like I said, you have these stacked wave functions. So how, ideally, in future work, is that f dry would really be a distribution of f dry. And then that would give me a distribution of Q. It's still small. It's still, I mean, like for my wave, like at least for my data, it's still small. And for the simulations we're running, it's within, like, I mean, we're getting good agreement for the steam water. What exactly the uncertainty is nominally, I don't know off the top of my head. But that's a good question. And that would be something to consider for sure. Yeah.
So what if I have a non-uniform heat flow? Your experiment is a uniform heat flow.
Yeah.
So what would happen if I have a non-uniform?
I have no idea. I mean, I feel like it would evaporate the same way, except you'd have a different sort of transport. So if you're a cosine profile, like for example, so basically you'd have a lot of vaporization in the center of the channel, not a lot of vaporization at first. So you'd have not a whole lot of dynamics happening at the inlet, not a whole lot of dynamics happening at the outlet if you didn't dry out, assuming you didn't dry out. You'd reach kind of an equilibrium state on either side. And in the middle, you'd have a lot of dynamics. So you'd have a lot of change in wave frequency, but the base film, again, remains relatively constant. So the wave frequency would certainly change. The waves would diminish because the waves are dumping mass into the base film. So the waves, you start to lose waves, and they also coalesce. Because as I lose mass from the waves, I lose speed. So it means the wave behind me now is a little bit faster than me. And if I already started as one of the slower waves, like they have a distribution, if I started on the tail end, I'm a little slower wave, and the guy behind me is a little faster wave, he's just going to catch up to me. And so you have coalescence, you have like basically mass transport from the waves. So there would certainly be a change in the wave frequency along the heated length, absolutely. And same thing here. Like the wave frequency certainly changes from the inlet to the outlet.
I guess where I was asking is that if you take in a non-uniform heat flux, can you take your approach and apply it there and see if you see a difference from the uniform?
If you also measure wave frequency.
Okay. So we're back to wave frequency.
Yeah, so if you can measure wave frequency accurately, or if you can model it accurately, then there's no reason it shouldn't apply.
I asked this question last time. I was wondering if you had thought about it some more. So, uncertainty. You spend a lot of time talking about transfer coefficient. What is the uncertainty?
Yeah, that is in the deep bonus slides, like 80 maybe. 80. Oh, yeah, here we go. So the way that, okay, so basically the way we get the heat transfer coefficient is using this thermal resistance network. And the biggest uncertainties in the thermal resistance network are this R test section. So basically, I had to estimate how much I lose like from the outward side of the test section. And then this external heat transfer coefficient, which is just a natural convection. So I just estimated that to be 10, and then back calculated what RTS is. So they both have like a 10%, like 10% uncertainty. But with that being said, that's the biggest part of the uncertainty. Oh yeah, so here. Yeah, so these are both like about 10%. With that being said, because under two-phase flow conditions, 99% of the heat is dumped into the fluid, I have still a very small heat, and this is for the average. So this is actually for including all the dry ones. So really, when I'm actually under two-phase flow conditions, and I'm not drying out, and I'm consistently giving it all to the liquid, and I'm near like almost all of my heat is dumped into the fluid.
I think my issue with this before was your temperature uncertainty. That seems extraordinarily low.
So they're
What if you, like, for example, I think more typical, like, thermocouple uncertainty, assuming you don't have a really, really fancy calibration setup, is more like 0.2. How would that impact your heat transfer coefficient?
I mean, well, in order of magnitude, I guess. Like 0.2. But no, see, it's different though because it's divided by delta T, right? So if I had a higher uncertainty in my temperature measurement, in this temperature, and these were calibrated using a water bath and a mercury thermometer, and like, yeah. This is, Tiago's did this. I mean, Tiago did it. Basically, we ran it up and down 100 times and took the standard deviation as the uncertainty.
But I think it's based on the uncertainty of the actual temperature of that thermocouple, not like.
Well, so that would be like what the manufacturer gives you, right? The manufacturer is going to give you the max uncertainty.
Well, you can calibrate it to
And
make that lower.
yeah, which is what we did.
Yeah, but I mean, like, you can have repeated measurements that are all the same, but they'll be off, right? Like, your standard deviation of your repeated measurements.
Then you have a biased measurement device, right? So then that would just mean then all my thermocouples are wrong. Like, so that would be the hypothesis.
Not like wrong. I'm not saying they're like biased by like 5 degrees. I'm just saying that.
But that, I mean, it would be noticeable, right? I would have a noticeable bias in at least one of them.
So I think typically, like, people, when you're calibrating thermocouples, I've never seen 0.05. So it's usually like about 4 times the uncertainty of the thing you're calibrating off of. So if you have a mercury thermometer, I don't know what the uncertainty.
It was a mercury thermometer and a water bath, and the uncertainty of the water bath was 0.01.
But the thermometer.
The mercury thermometer was 0.1. Was
but it was like just a digital, like it wasn't a digital thing, right? It was just.
No, it was a physical mercury thermometer.
Okay. I have some qualms about that low of a temperature uncertainty. Because it seems like your heat transfer coefficient uncertainty is, I mean, 1.5% is great, but like, I haven't seen people be able to measure that accurate of a heat transfer coefficient if it's really high. So it typically is much.
So this has also been corroborated, yeah, thank you, with the inner wall temperature measurement. So basically, I also compared this when I'm measuring the inner wall temperature using the thermal reflectance, and I compared my heat transfer coefficient and my wall temperature measurement with what I was getting using the thermal resistance network. And so I confirmed that my heat transfer coefficient was what I was estimating. Could there be a little bit more uncertainty here? I mean, I suppose, but I mean, this is again averaged over all the values where to the far right of this plot, I'm not going to do it, to the far right of the F dry plot, there's a huge uncertainty. And to the far left, when you just like first introduce heat, that delta T is so small you know, then any uncertainty in the temperature, and then now that delta T is really, you know, then there's an uncertainty too when you just start heating. So a big uncertainty when you just start heating, big uncertainty when you're drying out, almost zero uncertainty because all of the heat is getting dumped into the mixture. All the heat is getting dumped into the fluid.
And one other thing, so you talked about this heat transfer coefficient increasing over a very short period of time, but I think Jason has spent a lot of time thinking about how heat moves through that window, and you're measuring that outer side of it, so it's not really a steady state case, right? Like it's happening over a
It's all a quasi-steady state, yeah.
So what's the time constant of
It's about 5
heat
seconds.
flow through the window versus that fractional second that the heat transfer?
It's about 5 seconds. There's a about 5 second lag. A time average, yeah. But I compared it with the instantaneous to make sure I was getting the right value, like nominal value.
Yeah, yeah. I guess it was that one plot where you had like this spike for like very simple.
Yeah, yeah. Yeah, and so that instantaneous heat transfer coefficient where all of a sudden it's through the roof is really because I had a delta that was so small. Which probably, like, I mean, does it really reach astronomical values, or is that the point where I have film breakup? Like, it's somewhere in between there. Because I have to estimate, okay, at a certain level there's film breakup, and so there's a correlation that basically predicts 2 to 3 microns around there is when you break, so I use that. But if you get delta down to 2 to 3 microns right before you get breakup, you get this insanely high heat transfer coefficient, but it's for an instant. And so it actually doesn't really impact the time average.
I didn't realize. I thought it was measured data, not modeled data.
Oh, okay.
Does it make sense if you compare it to
And I should have shown the next figure actually, which was a simulation we ran that actually like had that smoothed out. Like it didn't just have that one point because of that one delta. It actually took into account like thermal storage in the wall. Any other questions on there? Jean-Marie or Jack? Hey, Jack.
No, I don't.
Is Evan still on there or no? No, Evan left. Okay.
One quick question, just following up on Evan's question about, you know, with the improvement of heat transfer, when you have very thin film, so I think it was slide 73 again.
Wow. I did not know that worked. That's cool.
Where you have that heat flux that goes, you know, through the roof, that's kind of what Madison was referring to as well. So that seems to happen when your film thickness, I think it was below 20 microns.
Yeah, that's the thermal boundary layer that I'm calculating.
Yeah, but I think if you go to slide 87 or something like that, when you show your like base film of like 5.
Oh, so
Is it basically lower than that?
It's lower than that. So
to be stable, or
base film is like delta M, and then delta T is to the Prandtl to the 1/3.
Okay, so that's not the same.
Mm-hmm. Yeah, but they're related, absolutely.
Because I was wondering, can you maintain a film in a stable way that is so thin that you have that like super high heat flux?
I don't know how.
In a region where it's too thin for it to be stable.
I think that, how are you, I guess in like Jason's, so in Jason's, I guess if you have enough flux into that region somehow to equal the vaporization rate to maintain a super thin film, then I would expect a high heat transfer coefficient. But how do you get mass into that region at the same rate at which it's vaporized is tough.
You did look at sensitivity to your threshold at one point and found that it didn't really matter because in the end you intubated over a tiny little time.
I'm talking about for Jason's stuff though, right?
Yeah, that was kind of related to what Evan was asking, if you were like behind an obstacle or whatever, you have a region where it's like a relatively big film. Can you just get to
Yeah. So I think and it seems, at least with some of his geometry, some of his obstruction geometry, it seems like sometimes it seems like you can maintain at least a small region behind that obstruction where it is just an extremely thin wake region, right? So there is some mass flux into that region, but how do you control that is probably dependent on the obstruction geometry and the flow channel geometry. I guess you could taper that too.
Okay, Pete, turn off your.
Yeah. All right, bye guys. Thanks for coming.
Bye-bye, Roman. Thank you.
Thank you. Yeah, he's at Westinghouse, Sweden. He works with a bunch of guys at KTH too. All right, Jack, I gotta kick you out of here. Thanks for coming. Tell Dorothy I said I love her. Like, you want me to fuck off? Oh, okay. Oh yeah, that's probably a good idea.